All right. So this section is Pythagorean Theorem, which again, most algebra classes will introduce this a little bit, or you'll at least have used the formula. And the Pythagorean Theorem applies to what type of triangles? It applies to right triangles only. Okay, and so when you're looking at the Pythagorean Theorem states that the sum of the squares of the two legs, a and b, is equal to the square of the hypotenuse. So the Pythagorean Theorem is a squared plus b squared is equal to c squared. And again, it's a pretty familiar formula used in math. Okay, so here's basically what the Pythagorean Theorem states or allows you to work through. So if you're given a triangle in which, let's say, you're given two legs of the triangle and asked to find the third side, in this case the hypotenuse. Again, it only applies to right triangles. And when you work through this, you simply take the sum of the squares of the legs, so in this case 1 squared plus 2 squared, set it equal to the square of the hypotenuse, again in this case an x squared, and then you solve for your unknown. So here if we simplify our powers, 1 squared is 1, 2 squared is 4, combine our terms, and then extract the square root. Now, when you extract the square root mathematically, you normally need to consider the positive and negative root. Okay, however, there's some restrictions on this because we're dealing with distances or lengths. Can you have a negative length? No. So we can disregard the negative root. So when we extract the square root, all we need to do is look at the positive root of that. And so our answer for this winds up being square root of 5. Okay. So now, in addition to be given both of the legs and having to find the hypotenuse, you might also be given one leg and the hypotenuse and be asked to find the missing leg. I want you to see if you can do that on your own. See if you can solve for y in this particular right triangle, please. Okay, so if you set up your Pythagorean theorem on this, you take your leg 4 squared plus your unknown leg y squared, set it equal to the hypotenuse squared, and then solve. Again, simplify your powers. You get 16 plus y squared is equal to 25. Move all your constants to one side, isolate your variable. You get y squared is equal to 9, extract the square root, and you get y is equal to 3. And now, did anybody get this answer without performing any of the calculations? Okay, so you're familiar with some of the patterns. We'll talk about that a little bit today. But what you notice here is you have this, the three sides of this right triangle are all whole numbers. They're positive integers. Whereas here, the three sides contain one irrational number, a number that can't be simplified into an integer. It's left as a square root of something. Okay. Anytime you have a right triangle where all three sides are positive integers, these are called common triples or Pythagorean triples. And I want to talk about these for just a moment. There's two very common triples. Okay, one is the one that we just saw, a 3, 4, 5. What that means is anytime you see a triangle, and again it has to be a right triangle, if the two legs are 3 and 4, you shouldn't even need to apply Pythagorean theorem. You automatically know, based on just the familiarity of this, that the hypotenuse needs to be a 5. If you were given one side, or one leg and one hypotenuse, and it fit this same pattern, a 3 and a 5, then you'd know the missing leg would be what? 4. Okay, now, what if you were given something where it looked like this, 3, 4? Would this missing side be a 5? No, it has to be the 5 would need to fall in the hypotenuse, and the 3 and the 4 would need to fall as the legs. Okay. There's another common triple that's often used, including being used on the SAT and the other standardized tests, and that is the 5, 12, 13 common triple. Okay, and so for the same kind of applications, if you see a triangle where the hypotenuse is a 13 and or the legs are 5 and 12, you can fill in the missing piece without having to complete the Pythagorean theorem because it'll always fit that pattern. 5 and 13 means our missing side is 12. If you have 13 and 12, your missing piece would be the 5. And again, if you had the 5 and the 12, your missing piece would be the 13. And so being able to work with these common triples can save you a lot of time. The SAT will undoubtedly have at least one of these, and usually it has a couple of them, because that test is designed for you to solve it or complete it without using a calculator. And so knowing these patterns can help save a little bit of time in working with those. Okay, now, in addition to just having the common triples, or again, they're also called Pythagorean triples, is you might have multiples of these. Okay, if you're dealing with common triples, it's not always going to be in the form of 3, 4, 5. It might be multiples of those. And so what that means is, if I gave you something where you had the following. Okay, 6, 10, and x. So here it's no longer of the form 3, 4, 5. But if you look to see, can you take and convert your given lengths into one of these patterns? Okay, so is there any way that we can get a 10 from either the 5 or the 13? Yeah, if we took 5 and did what to it? If we doubled the 5, we'd get 10. So we're looking at this potential multiplier of 2. What happens? What do we have to multiply 2 by to get a 6? 3. So what we do is we look at what's left after we consider the multiplier and see, does this fit the pattern of a 3, 4, 5 common triple? Yeah. So we can apply that and then just use the common multiplier for this. Here in this particular case, our multiplier was a 2. And so 4 times 2 gives us 8. So once again, you can mentally calculate this unknown side pretty easily using the common triples or the multiples of them. Okay, so what if I gave you this triangle? And see if you can find what y is. Just quickly, mental calculation. Okay, come up with the answer of 12. So here, in order to get either to move from a 5 or a 13 into 20, we simply take 5 and the multiplier is a 4. So let's test that. Does 4 go into 16? Yeah, 4 times. And so we have a blank 4, 5 that does fit our common triple. So this is a 3, 4, 5 with a multiplier of 4. So our answer, 3 times 4, or 12, would be that missing piece. Okay, now, do you need to know this in order to answer these questions? No. You can always use Pythagorean Theorem to confirm it. This, however, just allows you to do it without having to work with large numbers. Okay, so if I gave you something like this, okay, what would z be in this case? Z will be, here we have 2 times 13, 2 times 5, so we have a 5 blank 13. So we apply our common multiplier, we get 2 times 12, which is 24. Okay, so if you can work with those, there are more. Right? There's more than just these as far as the common triples. These, though, are the ones that are used the most often, especially on standardized testing. Okay, questions about that, Pythagorean theorem or the common triples based on that?